Well, welcome to the next installment. This lecture will concern itself with the mathematical notions and some very broad overview of the proofs. We won't get into the weeds on the proofs in the sense that a lot of it uses the insights of geometric measure theory and integral geometric measure and slicing decomposition of our functional associated with sort of image processing, but generalized now here to the case of special functions of bounded deformation. So we won't get into the weeds in terms of those things. Instead, we're going to do a sort of a top-down proof and show the major theorems used in establishing the results and distinguish them slightly from gamma convergence results because we, maybe those who know about gamma convergence, or if you don't know, one of the main features of gamma convergence is a convergence of minimizers. And here we don't need that. We're in the dynamic case, and instead we're more interested in compactness, and then the cluster points associated with this compactness in L2 we show are in special functions of bounded variation or deformation, and it's almost gamma convergence, but we don't need gamma convergence, but we almost need gamma convergence. So, but I'll be more specific about that, you know, in another hour. Okay, so we don't have to go there just yet. So let us start, and so we'll review then the boundary value problem and the setup that we had discussed or introduced last lecture. So we have the strain here. Again, it's the difference quotient. It's a directional difference quotient along the direction E, where E is the unit vector pointing in the direction of Y with base point X. And then we have our potential, and then we take its derivative with respect to the strain. And in this particular case, it's given by this, where f is the potential function and f prime is its derivative. This is the influence function. We haven't talked much about it, but it gives weight towards, here's the influence function, it gives a weight towards the potential connecting x to y. Okay, so maybe points closer in, y closer in, this potential is a bigger value, y further away, close to the boundary of the horizon, maybe it's smaller, and this is the potential right here. And we'll scale it with the horizon, okay? So we'll define it really on the unit ball and then rescale it. So we'll have a given potential, this influence function profile, and then rescale it to our peridynamic neighborhood. And so here is the equation of motion. Acceleration is equal to elastic force plus body force. This is the displacement field. Rho is the density. Epsilon is the length scale of non-local interaction. The neighborhood of non-local interaction will be a sphere of diameter of radius epsilon. That will be the horizon of. If you're a point further away than epsilon, then you're not interacting. And then the volume of the ball is just the volume of the d-dimensional ball, and that's that. Okay, so where this is the unit ball in d dimensions, and this is the radius to the dth power. And so here we're going to take d to be 2 and 3. So 2 in planar problems or truly 3-dimensional problems. Okay. Again, the force between this base point x and y for any point in the interaction zone is given for a fixed y by this curve. And r is a fixed value here, and this again was an inflection point of the, or if you will, it was the inflection point of the potential. And and here it's where the derivative vanishes. So for strains larger than this value, we're softening, and for strains less than the value, we're we're still stiffening. And right here is the critical value where we have 0 stiffness. Okay? Or we have the maximum force, excuse me, not 0 stiffness, but we have the maximum force per S. And then it starts to soften. So here we're increasing up to here. We get to here, that's our maximum. That's our strength. That's as strong as we get. That's the maximum force that will be exhibited. And then beyond that, we lose strength. The force required to pull it, a certain strain, becomes less and less. Okay, so it's losing strength. So imagine, let's see, something that you take and it resists for a while, and then it begins to yield. That's what's going on here. And for each y and x pair, we have this law. Okay, and again, like I had said before, we soften once this absolute value of the strain, here and here, once it gets bigger than this value, goes more negative here or more positive here. Once we get rid of that, bigger than that, then we start to soften. But up and through here, we're stiffening with increasing force. So this is sort of the unstable place where once you get soft, it's easier to pull. Okay. All right, and so then we have boundary conditions. Now we have non-local boundary conditions, and so we have our domain D on which the dynamics plays out, but then we specify our boundary conditions on a rind, if you will, of thickness alpha, where alpha is bigger than epsilon, so that on that rind, we specify a Dirichlet for this particular problem, a Dirichlet boundary condition. We could generalize, but I think it suffices for these problems to ask that our displacement be 0 in the rind. Okay, so normally displacement boundary condition is prescribed on the boundary of the actual domain. Here it's prescribed on the rind, and that'll do it for us there. And that way we can have our horizon with the diameter epsilon centered right at the boundary and still be defined. Okay, so our dynamics is still defined for points at the boundary. For points beyond the boundary, so the whole dynamic problem plays out on D, and we have the non-local problem on the boundary condition is on the rind. And then we we complement our dynamics, our boundary condition with the initial conditions, and here we have initial displacement and initial velocity. Okay. And these initial displacements, the initial displacement is consistent with the boundary conditions. And so what we're going to do is to talk about existence theory. We'll embed it, we'll talk about a space. And so we introduce the space of L2 functions defined on Rn, but we continue these functions by 0 outside D. Okay? So that's basically, or if you will, 0 in the layer DC. Okay, and so the initial conditions then belong to this space, L2 functions, which are 0 outside of D. Okay, and the initial conditions also belong to these. Okay, so they're consistent with the boundary conditions. All right. And now we want to talk about more about initial conditions. So imagine now that we have our dynamics, this acceleration equals elastic force plus right-hand side, and it's posed on D. Now we would like to specify more of the initial conditions. And in particular, maybe we would like to have an initial set of cracks. Okay, we would like to have an initial set of cracks. So U0, the initial condition, maybe we should say a little bit more about it than it's just in L2. Okay, so what we'll do, and I'll informally introduce this here, is we'll specify a crack set K and a displacement U0, and the strain will be defined off the crack set, and the elastic displacement can suffer jumps across K. Okay, and for linear elastic fracture mechanics, the total energy associated with both bulk elastic and surface energy for that initial displacement actually has a linear elastic fracture mechanics energy, which is here this is the strain tensor, this is the trace of the strain tensor, which gives you the shape, the volume change, this gives you the shape change, and we integrate that over the D, plus what we call the fracture toughness or surface energy, which is an energy per unit surface area, multiplied by the surface area of the crack set. And this is the Griffiths fracture energy right here. Okay, that's the Griffiths fracture energy. And these are the shear and Lemay moduli of the material. So we're assuming of the peridynamic material, which we had described last time as suitable moments of the peridynamic energy. And so initially then we can prescribe an initial displacement that has jumps. And these jumps correspond to actual crack, if you like. Okay, and so we can initially start our peridynamics off on a domain, a Schleidt domain, if you will, or a domain with slits in it, across which the displacement can suffer jumps. That's a fine initial condition for this problem, and then we can let the evolution evolve in L2. Okay? Okay. And it turns out that the class of functions for which this functional, just in general, if you plop the function in there and this functional was bounded, a class for which this is true is called the class of special functions of bounded deformation. Okay, and I will give you a completely airtight description of this set, but I just wanted to informally introduce it here. So I kind of like, I'm trying to introduce things in layers. You know, we'll see this again, but in a more mathematical way, but I'd rather initially relate it to the original, you know, the problems where it's motivated. Okay, so we'll come back to that. But the cool thing is that it's a countable set or a finite set of, it has a finite length or a finite surface area to the jump set, and away from the jumps you have this integrable, square integrable strain. Okay, and these are the classic derivatives here. These are classic symmetrized gradients of the displacement. Okay, and so this is the transpose of the matrix given by grad U0. This is the matrix grad U0. Okay, so let's just talk about informal again in modeling. So in particular, SBD functions belong to L1. And the set of discontinuities are described by actually a countable number of components contained within smooth manifolds. And this is the d-1 dimensional Hausdorff measure of each component. And the total jump set measure is given by the sum of these. And the strain belonging here, again, is actually related to the peridynamic strain. Okay? So this space is not arbitrary. The peridynamic strain, remember, was that difference quotient strain. I'll go back. Is this difference quotient strain here. So that's the peridynamic strain. And that, as we pick almost every point in T, and we shrink these neighborhoods as epsilon goes to 0, and take the difference between this and suppose U is you know, in SBD, then the strain of U in SBD, this difference quotient actually converges almost everywhere, okay, in measure to the actual symmetrized strain tensor of that deformation, okay? And here we say for almost every x, and that means then these sets have the Hausdorff d-1 dimension has 0 Lebesgue measure, so this is fine. So you see here that this peridynamic on SBD they're compatible notions. So it's a good space for peridynamics, or it's a compatible space, function space for this. So existence theory, the initial value problem for the peridynamic evolution, and we'll actually prove it. It's very, very quick proof. Has a unique solution in the space that is of maps, C2 maps from 0 to t in time into the space L2, 0. Okay, so that's the deformation for each t and 0t. This is a C2 map into the functions L0, L2, 0 here. And it turns out that this evolution is uniformly bounded in time by some constant c, Okay, and here the L2 norm is the usual L2 norm in X. At T appears here as a parameter. And C does not depend on E, epsilon, and only on the initial conditions in body force up to time T. Okay, and we'll see such things coming out. Okay, so the threshold strain, where the force begins to drop again, we will denote it by SC. Okay, and that will be R over line, which is related to the inflection point of the potential, divided by y minus x. And I'll be more precise about what R bar is. The fraction of points inside the neighborhood with strains exceeding the threshold is written this way. So this is, in some sense, a probability, but it's a percentage of y's in the domain for which the strain at y with base point x in absolute value is larger than critical, that it's softening. And here what we do is we have a weighted volume fraction, and we weight it by the influence function, and it's such that the measure of any set B, okay, is going to be weighted by this weight here. So in particular for the peridynamic H, this total weight is 1, okay, over this set here, over that set there. And the weight is exactly the influence function, okay, because that is measuring the relative importance of x minus y, the bonds at y, and whether they're playing more of a role in the stiffness properties or less of a role in the stiffness properties. So we look at the weighted sort of average of the bonds y for which the strain is bigger than SC, okay? Now we're interested in this set. We'd like to do some diagnostics, and the other thing is we'd like to really have an airtight definition for epsilon, okay? I mean, a real material property notion of epsilon, okay? And so I'm going to get that. So we define at least the process zone, that is the place where things are softening, and we are kind of up, it's up to us to say what that process zone can be, and in fact we can have some leeway. We can choose it to be any set of centroids X with neighborhoods for which the proportion of bonds larger than critical is some fraction, okay, theta hat, okay? So say 50%, okay, that's our process zone at 50%. 20% of the y's based on this measure are bigger than critical, okay? So basically we'll just say that the theta hat is the value, and the peridynamic process zone are all x's for which this quantity is bigger than theta hat. So a certain proportion of bonds have absolute value bigger than the softening value. And now we ask, well, what can we say about this set X for which neighborhoods about a point X are softening, or some proportion of these bonds are softening? And the answer is it actually depends on the radius of the peridynamic horizon. That is, the Lebesgue measure of this process zone, the set of X's, is bounded above by the peridynamic horizon multiplied by a constant that only depends upon the energy at time t put into the system. So at time t in the evolution, we actually have a bound on the Lebesgue measure that is bounded in terms of the process zone, which is bounded in terms of the size of the horizon, divided by the percentage of bonds that are softened, normalizing constant. And then this, as I showed before, is the value where you find softening. That's the strength of the bond. So F bar, I'll just draw that again. that essentially this value here, if I draw it like this, this is the value R bar over square root y minus x. Okay, where R is the unique root of, and then I think I'll get it right, it's F double prime R plus R F prime R equals 0. Okay, so it really has everything to do with this, and remember we have F y minus x s squared equals W. This was the bond potential, W epsilon, and when it was equals 1 over epsilon, and then we had a, I'll write it here. So we had a 1 over epsilon, and then we have a J y minus x over epsilon equals W epsilon S epsilon y minus x. Okay, so this was our potential. This is where the potential begins to, the force begins to soften, is right here. R bar is the root of this. This has everything to do, R bar has everything to do with the strength. and so that's what's sitting in here. And moreover, if you do a calculation, you ask, well, what is the energy necessary to soften the force between x and all points, y, inside the neighborhood? You get this nice clean formula. And so now you understand what epsilon is, okay? Now you understand how to pick epsilon, okay? If you believe this is giving you the physics here, then you can actually pick your epsilon, depending on how ductile or whatnot the energy, you know, how it works. So we actually have now a definition for epsilon, okay? And what we see here, the point here is that in this particular model, as epsilon goes to 0, more and more force is required to break bonds, okay? So it's more brittle in some sense, okay? For for larger value of epsilon, less force is required. So this is where the multi-scaling comes in. And again, Bjorn Inquist was talking about multi-scale problems of type A, where he showed the bow shock in front of a fast projectile. And there, the shock structure and what's going on inside that shock, okay, is on one length scale, and then the shock relative to the size of the blunt body traveling through the fluid is yet another length scale, and we have the same thing going on here. It's a completely different paradigm, but we have a multi-scale problem of type A. That is we have a localization of microstructure, okay, a localization of physical phenomenon. Okay, and this is what we see here in this formula. And in paradynamics in general, they don't bother, they don't correlate, they don't do that. Okay, so in this is a multi-scale type model of paradynamics. Okay, and we'll show that. And it's a simple consequence of Grunwald's inequality and the energy. We're only putting in a finite amount of energy, so I'll show how that works. And of course, our hypotheses on our potentials. Now what we'd like to do is we'd like to understand what is happening as epsilon goes to 0. So we look at a family of solutions to these problems, of these dynamics, for, let epsilon k be 1 over k, for example. Okay, so we take and we send k to 0. I mean k, well, we send epsilon to 0 and we send k to infinity. And we do make one hypothesis. Okay, we will suppose that the displacements are uniformly bounded in L infinity, okay, for all epsilon. That is the one thing we will ask, okay? And I believe it's possible to introduce generalized, we have to go through Dalmaso and details, but I think we can introduce generalized special functions of bounded deformation and work on eliminating that hypothesis. But for the moment, we keep that uniform boundedness in there. So we assume that. Then we have the following. For each epsilon k will prescribe identical linear elastic fracture mechanics initial data. So we'll start with an initial system of cracks as specified in the initial data. And then we will pass to a subsequence if we have to find that the cohesive evolutions in this subsequence converge in mean square uniformly in time to a limit evolution U0 that belongs to the set of continuous maps from 0 to t into L2 0. With the same, these U0s will have the same LFEM initial data. And so what we mean is that we can, for this evolutions here, we can always find a subsequence in the cluster point, U0, such that the evolutions are converging to it for almost every time. Okay. And in addition to that, the limit evolution will have a weak derivative also belonging to the product space. Okay. So we have a compactness. So we have at least one cluster point for a sequence U epsilon converging, or U epsilon k. We have at least one subsequence that converges to something. So we have a cluster point, and we could have many of them. Okay, but we have at least one. Now I'm going to get into SBD in earnest. Okay, so functions that are special functions of bounded deformation, they belong to L1 and are approximately continuous, with the usual notion that almost everywhere you take a ball of size epsilon, you send the radius to 0, then these UYs, that goes to 0. So that's the Lebesgue differentiability. Okay. And the jump set for the elements of special function of deformation, special functions of bounded deformation, is defined to be the set of points of discontinuity which have two different one-sided Lebesgue limits. Okay, so a one-sided Lebesgue limit, you're familiar with the Lebesgue limit, and a one-sided Lebesgue limit is just what you think it should be. You have your ball of radius epsilon. Here H epsilon just refers to a ball of radius epsilon. It could be a peridynamic horizon, but right now it's a ball of radius epsilon centered at x. And then what we do is we take a plane with normal nu. Okay? And that normal depends on your position x, where the center of the ball is, right here. Okay, so we take a plane with normal nu, unit normal nu, cutting the ball at x, and on one side we consider shrinking the ball and just looking at one side at x as we shrink the ball to 0. That'll be the plus side, say. And then the other side, the minus side. Okay, and that has to do with traversing the curve. Okay, so we'll go, I think, this way on the curve. So that's the usual. And so then we have these one-sided Lebesgue limits, which are, oops, we'll go back here, which are given by h minus epsilon, okay, which is associated with the set of points to one side of the plane, and h plus epsilon, which are points on the other side of the plane. So h plus are the limits associated with right here, and h minus are the limits associated right here. And these are called the one-sided limits, u prime. So if any these integrals over the half balls determined by the unit normal, and we have f u0 u plus there. So those are the one-sided Lebesgue limits. And these are called jumps, okay, with respect to this x, this point x. And the amazing and nice thing about SBD functions is that the jump sets are exactly the collections of x for which you do have a jump, a u plus and a u minus at x for some direction, and they're glued together. So the nice part about it is that SBD functions have jump sets described by a countable number of components, each of which is contained in a smooth manifold, with the exceptional set K0, which has 0 d minus 1 dimensional Hausdorff measure. And the total Hausdorff measure of the jump set is just the sum of these countable components, the countable sum here. Excuse me, the strain of this displacement belonging to SPD is is a generalization of the strain tensor, and like I said before, it's related this way. And we actually have so those are some fine properties, and then we also have that the symmetric part of the distributional derivative of U when we're in SPD is a d by d matrix valued red on measure with absolutely continuous part described by the density here. This is the absolutely continuous part with respect to Lebesgue measure, and the singular part with respect to Lebesgue measure is given by the jumps over the jump set, and we integrate against d minus 1 Hausdorff measure. So this is the weak derivative, and the weak derivative of an SPD function, we only consider its symmetric part, okay? And the symmetric part is what we consider, and there it has two components: a jump and the absolutely continuous part. Now, general say BD functions, okay, they also have a Cantor part, okay, another singular part in addition to the jump part. But we throw that out, and the Cantor part is diffuse and spread out. This is concentrated on jump sets, and this is what we use. Okay, and a lot of the fine properties of SPD functions are established in Dalmaso, Cosico, and Ambrosio. Okay, and then there's an earlier work of Dalmaso and Bellatini, which also starts to, which goes on a long way to prove the finer properties as well. And I will put both of those papers in the references. So I should also mention that the BD functions were originally invented or proposed for plasticity by Pierre Souquet, and then rigorously there were several people that proved the kind of theorems you see in Evans' fine properties of functions in SBV for SPD, like Roger Tamam, okay, had proved for Lipschitz domains some approximability by smooth functions of SPD. Okay, and then most recently these finer properties are coming up. Okay, SPD2, which is often written this way, is simply a subspace of SPD with both U and the absolutely continuous part belonging to U belongs to L2, and the absolutely continuous part is a symmetric matrix, and so the absolutely symmetric part belongs to L2 where functions where we're in symmetric matrices. Instead of vector valued functions, we have symmetric matrix valued functions. So that's called SBD2. So we have the following. The limit dynamics has bounded linear elastic fracture mechanics energy. And we do assume, this is our assumption, that our initial datum is in L infinity. Then the limit subject to our hypotheses on uniform boundedness in L infinity of our solutions for every epsilon, U0 belongs to SBD. For almost every, for almost every t and 0 t, and furthermore, there exists a constant depending on the time, the final time, bounding the linear elastic fracture mechanics energy of the limit. Okay, and these numbers here, again, fracture toughness, the Lemay modulus, and the shear modulus are the ones that we computed yesterday. Okay. And so we observe that then the limiting fracture surface is bounded. Okay, so this is the Hausdorff measure of that set. Okay, and it's bounded. So for each time, J of t, it denotes the evolving fracture surface, the jump set. Now notice we've gone from dynamics, cohesive dynamics with softening bonds, to a sharp model, okay? And again, here's the data, here's the shear, and this is in dimension 2 and dimension 3. And again, we have that mu equals lambda in both cases because this is a 2-point potential, okay? And I spoke to, I was speaking with John Hutchinson, and he said this sounds more like solid quantum physics or atomistics. You know, you have potentials and you have your theory. Well, in some sense, it is a little bit like that. So again, and just for completeness, the evaluation of the fracture toughness, again, was understanding the amount of work to separate the interaction of points on this side of an interface with the interaction of points on this side of the interface. And again, we were only doing it for all points transverse to the interface. Okay. And so we did that calculation before. And then again, for the linear displacement, if we assume that displacement is linear over the peridynamic interaction zone, then we quickly find that the energy density is actually given by the elastic energy density. Okay? And here I have to, there's a typo. I should have another F here. Okay. And so the elastic energy density is given by the this is the symmetry part, and then this is sort of the shape change part of the elastic tensor, and this is the volume change part. Okay. So again, the absolutely continuous part of the strain is defined for points away from the fracture surface. For the limit evolution, it can be confined exactly to the fracture surface. And the theorem shows again that the fracture set in limit evolution is, for the limit evolution, is d minus 1 Hausdorff measure. So for the case where we didn't take epsilon to 0, we had a process zone that was vanishing Lebesgue measure as epsilon goes to 0. And here in the limit case, we see that the process zone and everything is collapsed down to a sharp interface. Okay. Then we actually have an energy inequality. That is, if we do accounting, a bookkeeping. If we do some bookkeeping, and we say, well, what's the energy in the limit evolution? It's the kinetic energy plus this energy due to elastic deformation and creation of surface minus the work done against the load at time t. And then what we have here is the initial data has the same thing, the kinetic energy, the initial velocity, the initial LFEM energy, and the initial work done against the load. And you can show an energy inequality. That is, for almost every time, that the energy at time t is bounded above by the energy due to creation of surface, elastic energy, and kinetic energy. And this is the contribution of the external forces up to time t. And we have this inequality, which is consistent with the second law. So this, if you're going to get an inequality, this is the one you want. And then we do have an inequality here. And to understand if it's equality or not, we have to dig some more. So right now we're missing at something. Okay. All right. So, but this is what we find. Now, away from the fracture set, if we're in a quiescent region where D prime is an open subset of D, and these do not belong to the process zone, so the stress is less than SC. And this is true for all times, and for sufficiently small epsilon k's. Then if this is true for every x, and then we have a little rind around it of epsilon k and y's, for which x minus y is less than epsk, then the limit evolution evolves elastodynamically inside the quiescent zone. So we don't have any fractures there, and we can pass to the limit, and we actually get that the limit evolution satisfies the Navier-Lamé system, the usual classic elastic system, where here this second derivative is in the sense of distributions, okay? And again, the stress tensor, the derivative of the stress tensor is in the sense of distributions. And the stress tensor is given by the shape change, which is the trace of the absolutely continuous part of the symmetrized gradient, which in this case is actually everywhere. It's defined everywhere. And in this case, or almost everywhere again, and in this case, we have the, this is the volume change, and this is the shape change. Okay, so we actually have that away from the fracture set, we have the classic wave equation. Okay, so what I'd like to do, I'm actually going fast, maybe that's good. What I'd like to do is just outline some of the proofs involved in the previous statements, and just show you or give you a landscape of what's required here, without getting into the weeds. Okay, so just give you an overall idea of what's going on. So we want to prove existence of the peridynamic evolution at fixed epsilon k. So that's a second order evolution, and so we'll turn it into a second order in time. We'll turn it into a first order in time evolution. So this is a lot like what Rob was referring to yesterday and the day before, turning second order evolutions into first order evolutions. So that's a natural thing to do here. And so we introduced a system of involving two vectors, or two vectors, and the first vector is the deformation, and the second vector is the velocity. And then we set this vector valued function here of the vector at each time t to be given by these two components, where the first component is simply y2, and the second component is the peridynamic force acting on the deformation, y1, plus the body force. So we turn it into a system, and we actually then can rewrite the second order system as this first order system. Okay. And in fact, then we take our initial conditions to be consistent with linear elastic fracture mechanics initial data. On the other hand, SBD fits right into SBD2 fits right into L2 0, so we could actually consider L2 initial data, displacement and velocity. So more generally, we could consider that. And then we have an existence theorem, that there exists a unique solution. C1 maps from 0 to t into the space L2, and described by this dynamics here. And the body forces, we will ask that the body force, which is wrapped up in F, in the description of F, be a C1 map from time into L2. So there exists a unique solution for this first order system. So that's how we prove, or that's how we show existence. We show existence for the first order system. And the proof of this requires a calculation, a bit tedious, but a calculation that shows that the supremum of the second derivative of this function is actually bounded. It's a function of epsilon, so we see that as epsilon goes to 0, this bound gets worse and worse. But what we get here is from this fact here on the function itself, then we actually can translate that calculation into an L2 bound. And here L2, what I'm talking about is that when I say a function w in L2, I mean its first component is in L2 and plus its second component is in L2. So f here is a two-component vector function. And so in this norm here, y and then z, t is the same for every t in 0t, and we actually have that this is a Lipschitz continuous map. So the right-hand side of the ODE is a Lipschitz continuous map in L2, and the Lipschitz constant is c upon e squared. Okay, so we have, for a fixed epsilon, we have existence of our ODE flow. because of the uniform Lipschitz constant on this space L2. Now notice that the Lipschitz constant goes bad as epsilon goes to 0, which you would expect because you see that the limit point is going into SBD and you have jumps. So you don't expect some sort of continuous possibly thing, okay? So that's what's happening here. And I'll make that even more explicit because in the next lecture I'm going to do numerical analysis and get convergence rates for finite difference schemes for this kind of evolution. And there we're going to instead assume our solution doesn't lie in L2, but we'll suppose our solution is in a Holder space, okay? And actually then we show existence and uniqueness again of solution in Holder space, and we will show convergence of finite difference schemes in L2 to these Holder solutions, okay? Again, though, you will be able to show that the Holder convergence, that these Holder solutions, as epsilon goes to 0, converge. Again, you can find compactness, and there's a subsequence converging strongly in L2 to a limit, which lies in SBD. Okay? So it's very interesting that you really don't need discontinuous functions to begin with in your peridynamics, which from numerical simulation means is good. You'd love to have smooth functions, and you can approximate them nicely. Okay? And then in some limit, yes, you get a crack. So in a sense, this is going to be a regularized scheme for computing cracks. Okay, so anyway, this is the existence theory for L2 solutions of this dynamics. And what we did was we wrote it as a first order system. Saw that the first order system, the right hand side, was uniformly Lipschitz in time for these L2 evolutions. Now, so we have existence. So we now know for each epsilon we have a solution. Now what we'd like to do is proof of compactness. That is given some family epsilon k of solutions, which we know exist, we'd like to say that this family, actually this collection of as epsilon goes to 0, this sequence has cluster points, at least one, okay? And then that cluster point automatically has more regularity, lies in SBD. But first we do compactness, okay? So this is how it goes for dynamic problems. First we do compactness, then we show that the limit points automatically have some higher regularity. And that's what we need. And then how we show this, I'll show you now, is how we show this, okay? And I won't get into the weeds on the details of how you show it, but how you show it is important, okay? So what we would like to do now is do our L2 compactness uniformly in time. Okay. So the way to do that is we need first off, for these flows, we need a uniform bound in time on the, and in epsilon, on the peridynamic energies and the kinetic energies. And C can only depend on, say, the endpoint T. Okay? So that's the first thing we need to get in order to get compactness and also higher regularity. Okay? So this is how it goes. So basically what we need then, if we're going to get a bound on the elastic part and the kinetic, is, and we have a first order system or a second order system, we're going to use, as everybody probably studied out of their favorite PDE book, a Grunwald inequality for the wave equation, only now it's a Grunwald equality for a very similar looking type of equation. So you multiply both sides of the dynamical equation, which was given by this. I actually almost have it right there, but I'll write it again. So we have the equation. We can rewrite it this way: grad P E of U epsilon plus B equals rho dt T of U epsilon. And now if I multiply both sides by u epsilon of t. Okay? So we do that, and then we integrate. Okay? We integrate. And so that's what's done. That's what's done here. And basically, I'll just put it back up here. I just reoriented terms. I put the b on one side and then this on the other side. And so what we get is when we do that, we get this. This equals that. So by multiplying both sides, we get this equals that. And we observe what this is. This is nothing but the time derivative of this. Okay, so that's all you do. Okay, and now we're off to the races. We just use the Cauchy-Schwarz inequality here on these two guys. Then we identify W of t being this object here. Okay, so we get that the time derivative of Wt, given by that term there, is less than or equal to the L2 of the time derivative of u times b. And we just write it out. Well, that's equal to this quantity W of t, okay, here. And the reason it's less than or equal to is as I have a derivative. So if I define Wt of this being 1, its derivative, that goes away. And so that's fine. So we have this inequality here. Okay. And notice here, I really, I'm going to be dividing in a second by square root of Wt. And really, these two quantities are positive, so I could put an arbitrarily small number here. I put 1, but I could put an arbitrarily small number there. And then we continue. What I want to say is we basically want to get a bound on this. And that's going to be our Grunwald inequality. Okay, a uniform bound on that. Okay, so we go ahead and we divide by W of t, and we still have this differential inequality. We use the fundamental theorem of calculus. We have this, and then we move W0 over to the other side, and we get our inequality. Okay? Now, W0 is the initial data, and W0 is just, W0 is when I put the initial data in here, U0, which is the same for every epsilon, and V0, which is the same for every epsilon. And now, what we have to do is we have to get, if we put U0 for every epsilon here, we would like to get an upper bound on this. If we get an upper bound on this independent of time, okay, or independent of epsilon, it'll be independent of time because it's going to be U0, but independent of epsilon, we'll be in good shape to prove this thing, uniform bound here. Okay, so here we already have Grunwald's inequality. Well, we couldn't move to get Grunwald's inequality. And so then the next thing is we would like to show that if you have any u, which is an SBD, this is a fundamental estimate. The actual peridynamic energy is bounded above by the energy of linear elastic fracture mechanics for every epsilon. In particular, then, you could put in U0. And you see now that when I put in U0, I get an upper bound for every. And so this is the elastic for the LEFM. Okay? So we actually have this. Okay? This follows from, this is a theorem, and one has to prove it, and it comes from image processing, basically, but it's adapted to the case at hand. So we can use a scalar. We have to do a vector version of this, which requires its own techniques, but it's the scalar version you can see in the work of Gabino, Massimo Gabino, and also in one dimension it's described subsequently in the lecture notes of Andrea Brady's, and I will provide those references. It's also completely done in this paper that was written by myself in Journal of Elasticity for this case. So you can see how everything works in detail. So anyway, we have a upper bound on the peridynamic energy for initial data in terms of the linear elastic fracture mechanics energy. And we picked our initial data to have bounded linear elastic fracture mechanics energy. Okay? So that in itself then gives us this bound. That gives us this upper bound here. Because we can just plug in what W0 is, an upper bound on W0. Okay. All right. Now, what the next thing we need to do, okay, so that's step one of compactness, getting a uniform bound, okay, on our solutions. The next thing, and again, I wanted to say one thing, is that what we just proved is that for every epsilon, independent of epsilon, we have this upper bound, and that's essential. We'll come back to this in a minute. But now we go and do something else, just in preparation. And we show that once we have the upper bound, now we go and do something else, and that is we show Lipschitz continuity of the L2 norm uniformly in epsilon. So there actually exists a Lipschitz constant that is independent of epsilon, for which the L2 norm here is bounded by the difference in times. Okay, and the important part here is that K is independent of epsilon. And the way we do it, and it's so easy. I can write this one out with and it's fun. Is you have your L2 norm here, and you write using the fundamental theorem of calculus the difference this way, okay. And then what you do is you multiply and divide by 1 over t inside the integrand, and you take that out, and you get a squared, and you get that. Then you apply Jensen's inequality here, and you get that. And then you go ahead and what you do here is you use the fact that this here gives you this gives you that, and then you exchange using a Fubini theorem, and this gives you the L2 norm squared. And then finally we have a uniform bound on the derivative, time derivative of u from here. Oops. Not yet, I'm going the wrong way here. Let's go back the other way. Right here. So we have a uniform bound on the time derivative. Okay? So we finally, and that comes from Grunwald. So we finally establish this. Because this is uniformly bounded. We get an extra power of t minus t1 minus t2 there, and you get that. Okay, and the cool part is that K is independent of epsilon because we got this bound. Oh, I'm going the wrong way again, sorry. Because this bound, oops, I'm still going the wrong way. Because this bound is independent of epsilon. Yes?
In your existence proof, is the interval of existence, does it depend on epsilon?
No.
Because your Lipschitz constant will depend on epsilon?
No, for fixed epsilon, you have existence. So for every epsilon, you'll have existence anywhere, in space. Yeah. So there's no finite time. So you could have arbitrarily large time intervals, and you have existence. You have a lousy Lipschitz constant, but that's the key. We want to get away from that and get some sort of uniform bound that doesn't depend on epsilon, and we do that using Grunwald inequality. Okay, and the fact that the amount of energy available to the system is of some fixed amount, and because of that, then we can do this sort of thing. So it's an energy argument that says it's independent. We get this independence. Okay, so these are very simple, real and calculus things. And now what we want to do is we want to show compactness. Okay, uniform compactness. And what we'll do there is we'll just use the Ascoli Theorem. Okay, how do we use the Ascoli Theorem? The following. For each fixed time, we have the following nice result. That if you have a sequence of functions in L2, and they're denumerable, and the supremum, they're bounded, that this quantity is bounded, that the peridynamic energy is bounded and the L infinity is bounded. okay, by some number, we have a compactness, that there exists a subsequent and a limit point for which this goes in L2 as epsilon goes to 0, okay? So we actually have at each time a compactness, okay? So this is a theorem. So this is a new thing you have to dig out of the peridynamic solution, but because of these peridynamic equations, we have it, so there exists a limit point. Then we can use the previous thing, which was this Lipschitz in L2. So we have pointwise convergence in L2 because of compactness, and now we have the uniform Lipschitz condition, and so as we do on the real line, we can use Ascoli's theorem, and we get a limit evolution exists, okay? So it's just like the 1D proof on the real line. The miracle is to get this and to show compactness at each t. So we've got that. So now we know that the sequence as epsilon goes to 0 has limit points, has cluster points. Now the question is, we'd like to characterize those cluster points, okay? And so each cluster point we now show lies in SBD, special functions of bounded deformation, and our hypotheses bounded in L infinity. That for almost every time, or actually every time, I should say every time, the limit it belongs to that, and furthermore, there exists a constant depending on t for which this holds. So this is the higher regularity of limit points, okay, or cluster points, higher regularity of cluster points. So they lie in SBD, and their linear elastic fracture mechanics energy is bounded, uniform, okay? And what we do is we actually have this higher regularity. So if we know we have a limit point, and we know that the supremum, we have a bound here, then we can claim, this is a theorem, that the lim inf of these energies, as we go to the L2 limit, converge strongly in L2, we actually find that our U0, which is the strong limit in L2 of U epsilon, actually is in SBD and has bounded linear elastic fracture mechanics energy, okay? And this has its origins in the slicing theorem for Mumford-Shaw non-local energy functionals, and construction of a suitable sequence that's actually a little bit smaller than U epsilon, okay, which actually lies in SBD on slices. And then you glue it all together using a structure theorem of SBD, and you can get this. Okay, and so all that's done in detail. And the basic strategy for doing this comes from the image processing literature and the work of Massimo Gobino. Okay, but you can take all of it and you can upscale it and do whatever you need to do. Not upscale it, but extend it, do whatever you need to do, and you can actually get it for peridynamics. Okay, and that's the important part here. So we actually then have that the limit points, or cluster points, L2 cluster points, actually belong in a more regular space, SBD, okay, and have bounded linear elastic fracture mechanics energy, where this is bounded above by our earlier work. Okay, so, okay, now, what I want to say is so those two theorems that I just showed you, existence of cluster points and regularity in SBD of cluster points, if I parse it slightly differently and add one more thing, I actually get gamma convergence, okay? Now, why I didn't say gamma convergence here is because we don't need gamma convergence. We just need what I just said. But those two things are integral parts of gamma convergence argument. Now, gamma convergence is important if you're looking to see functionals that have minimizers. So at each epsilon, you have a functional f epsilon, and it has a minimizer. And then you'd say, well, these F epsilons, epsilon goes to 0. What are the minimizers doing? Well, gamma convergence tells you. Here we have a dynamics problem. We don't care about minimizers, okay? We care about compactness and higher regularity, so we use what we need, okay? But if we add one more little thing to it, then we get a gamma convergence. Gamma convergence is huge in the quasi-static fracture literature and the model of Frankfurt and Marigot, okay? That's huge there because they work with local minimizers and they're very concerned about it. Here, we're doing dynamics. The other sometimes little problem that happens is people are often wondering about gamma convergence in dynamics. Well, they're kind of not relevant, okay? Pieces of the gamma convergence estimate are relevant for dynamics, but other pieces are not, okay? So when one wants to say that, they're always worried about dynamic. Now, if you do have local minimizers and you're doing dynamics, gamma convergence is your thing. But here we're not, okay? And so in the fracture community, there's always been this confusion about local minimizers versus global minimizers, and gamma convergence works for global minimizers. Gamma convergence doesn't work for local minimizers. It's been updated, so it does a little bit in certain cases. So I have, but anyway, it's not relevant for us, but yet it's known and everybody should know it. Okay, so here I say it, okay? So because in the non-local image processing literature, you'll see gamma convergence. In what we're doing, we don't need it. Okay, and now I just want to make that big distinction for you so you can talk to people in different disciplines. Okay, so let's say what gamma convergence is, and then I'll say why you want it and when you want it. So we have a sequence of functions defined on a metric space with values in the extended real line, together with some sort of what we're going to call target function, also defined on that metric space on extended real lines. And we let X be a subset of that metric space. So we have all kinds of notions of convergence, pointwise convergence, uniform convergence. Here's another one called gamma convergence, okay? So it's a very general idea, but you can exhibit, and there are many nice, what I will say, examples where you have sequences that pointwise converge, but maybe they gamma converge, but they don't pointwise converge, okay? So there's, this is a nice topology course thing that you could introduce. So F is said to be the gamma limit of a sequence of functions with respect to the metric on a subset if the following two properties hold. For every X in the subset and every sequence converging to X with respect to the metric space, we have this sort of lower semi-continuity. So Xj converges to X, and the lim inf of these functionals evaluated, or functions evaluated, Fj at Xj, are that. So it's kind of lower semi-continuity, if you will. Then for every X in the subset of the metric space, there is a recovery sequence, okay, such that the limits match. If you have that, then one says that Fj gamma converges to F on the metric space in the subset, okay? Now the great thing is if, for example, and I don't show it here, but I'll just state it, that if you know that X actually is a minimizer for Fj, or say Xj is a minimizer for Fj, then you know that these minimizers Xj actually converge to a limit X, which is a minimizer for the limit functional. And that's very important to have. You have this sort of preservation of minimizers. Okay, and this is a beautiful convergence, and it's used everywhere to prove all kinds of wonderful things, multi-scaling things, okay? And in particular here, it does apply. We can actually show we have gamma convergence, although we don't need it, okay? But we have it, and so I wanted to make that point. What we need for this problem is compactness and higher regularity. So for you in this subspace, L infinity of this space, we define the Griffith fracture energy to be the linear fracture, elastic fracture mechanics energy, if U belongs to that, and plus infinity otherwise. We find that these peridynamic energies gamma converge to the Griffith fracture energy in the sense that this is a gamma limit with respect to the metric on L2 and converges on the subset L infinity. Okay? And there, what we are lacking, what I have not shown you is I've shown you this part, and this part I haven't shown you, but I'll tell you what it is right now. What is the recovery sequence? Take any x in L infinity and L2, which lies in SBD. It's its own recovery sequence. That if I plug in x here, I get fj of x equals fx. Okay? So that is that that initial data is, if it's in SBD and it's in L infinity, we just repeat, the sequence will be the function itself, and we recover it in the limit. Okay, so that's the recovery sequence. So with that, we actually establish gamma convergence. Okay, but the point being is that we don't need gamma convergence in this dynamic context. Okay, now what you can do though is you can go ahead and look at problems that do have gamma convergence, but also as part of that, you tease out that the limits are in SBD. And so we can apply these techniques to dynamic phase field models based on Ambrosio-Tortorelli potential for fixed what they call a regularization parameter appearing in the Ambrosio-Tortorelli functional. And so in these phase field models, you have a phase which represents damage or softening, and then which is a field, and then you have your deformation field. And so many dynamics here in this thing, they have done dynamic experiments at fixed epsilon. Well, they never passed to epsilon equals 0. But you can use these techniques here to pass to epsilon equals 0 and show that their methods are actually converged to a sharp interface model, which is given by the energy of linear elastic fracture mechanics. Okay? So they just didn't know about this other stuff, this compactness and high regularity, but you can apply it to their method too. Okay? All right. So, and you can also apply it to the methods of Tom Hughes and Bourdin, not Bourdin, but another Bourdin. And they have what's called a phase field model. They call it that. You can apply it to that, and you can apply it to the work of Mary Wheeler and Thomas Wick and Andro Mikulich. You can apply it to that work, although not to the poroelastic evolutions which they do, but just simpler case. So the last thing I want to do, I was just talking on the topic of gamma convergence and weak convergence, so I'd just like to talk about weak convergence for a minute. So remember, I got away from the fracture set in the quiescent region. We have that the peridynamic evolutions converge to the linear elastic wave equation. So I wanted to show you on the face of it how that goes. So we have our peridynamic strain here, and what I've done is I've rewritten, I've written y now. Y lies in an epsilon neighborhood of x, and what I've done is that I've rewritten it as I've rescaled things instead of being on the epsilon ball to the unit ball. So y now becomes x plus epsilon of xi, where xi lies in the unit ball. So I've introduced this new parameter xi, which lies on the unit vol. So this is y, this is x, and this is x minus y, but in new coordinates. Anyway, I rescale it. It's still the same peridynamic strain, and here I've written it in this fancy difference quotient way. The weak form of the evolution equation, again, put the time derivative on the test function. This is in space-time. So this is a lot like what you saw a day ago about space-time formulations. Okay, and so, but here we're using it differently. We're looking for weak limits in space-time. So we have our dynamics now in weak form in space-time is we put one time derivative on the test function, a time derivative on our solution. Okay, so our solution satisfies this for every test function. And what I've done here is I've written out the gradient, what I used to call gradient of peridynamic energy. I wrote it out in this particular way, but it involves, again, the stress. The strain, the peridynamic strain. And here's the test function sitting right here. And this is the difference quotient acting on the test function. And here we have integral over the, notice here I've changed from the epsilon neighborhood of x to the 1 neighborhood of 0, consistent with my change in coordinates, but this is more or less, this is exactly the evolution equation now, satisfied again by the peridynamic evolution u epsilon, u super epsilon k. This is the body force. Now the key here is that this force, the peridynamic force, is given by f prime, and then inside is this, and then this is the, so this is ds of w. This is still ds of w, the derivative of the bond potential with respect to strain. And now what we'd like to do is send epsilon to 0 and see what we get. Okay? The problem is that this is a non-linear quantity. Okay? Now what we can actually show is that as epsilon goes to 0 here, that S epsilon k converges weakly to a limit in L2 on x cross this H1. Okay, so we have that S converges weakly to a limit in L2 on this product space, but this is a nonlinear functional. So usually nonlinear functionals composed of weakly convergent sequences are tough to understand what their weak limit is, because you got a weakly converging sequence, you got a nonlinear functional, you take their composition, now you're looking at the limit of that. Okay, and it's not necessarily the case that the weak limit of that is going to be whatever that functional is evaluated at the weak limit. In particular, this functional changes with epsilon 2. Fortunately, the nonlinearity saves us, and it's a matter of calculus. A miracle occurs, okay, and you can pass the limit here using calculus, okay. And so here's the lemma. So right here for any test function. So if we know our peridynamic strain is bounded less than SC, and we know for the following that we can pass to a subsequence for which this is actually the absolutely continuous part of the measure of the limit deformation. This goes weakly in L2. Cross, I should have here cross, that's okay, it actually goes weakly in L2, you can say it this way. Then for any test function, this nonlinear function which depends on epsilon, this weakly converging sequence, that this thing as epsilon goes to 0 goes to the weak form of the, this is the test function, the symmetric gradient of the test function, and this is the strain, the stress, the elastic stress. It actually, this nonlinear thing actually goes to that, and because of that, then you recover the weak form. This will go strongly, u epsilon goes strongly to this. That nonlinear mess goes to that. It's actually not a mess. It's actually very nice, okay? But calculation shows it goes to this, and then you get that. And in the limit, then in the quiescent zones, you get the wave equation. So this is a real example, again, of multiscaling, okay? That is that a wave from, we had our non-local domain with things connected elastically by stiffeners, so by bonds, and we converge in the limit as epsilon goes to 0 to an elastic thing, okay, where we can actually write the formulas out for that. Okay, so that's the weak limit here, the calculation. I haven't gone into it, but I'm here for a month. I'd be happy to show anybody who wants to see it, and it's all written up in this article in Journal of Elasticity, down to the periods. So any questions? Because I've left a lot out, but no.
Another question, in your definition of SPD, the space, you have this normal vector field U. So is it always fixed, or do you say I just have to have some U?
Oh, yeah. So basically, no, it's not fixed. So it's basically, you just go ahead and you test. So, suppose we have an SPD function here, u of x, okay? And x belongs to D. So we go over to x and we look at it, okay? And then we take a plane with a normal nu x, okay? And we test it, and we see if the limit on one side is different than the limit on the other. If it's not, okay. But maybe for some nu, it is, okay? And that will be called the jump, okay? That'll be the limit, okay? The half limit, the jump, okay? Now we ask ourselves, well, let's look at that collection of x's for which such jumps exist. And we find an amazing structure with SPD functions. They're connected. Okay, they're connected by in 2 dimensions, a rectifiable curve, or in 3 dimensions, a surface. It's rectifiable. And they are, okay? And that's called the fine property of SPD, and that is a very delicate theorem, okay? That such an amazing thing occurs for something with a radon measure. But this is introduced in Ambrosio, Kosaka, and Dalmaso, and also preliminary. It's also introduced in the work of Dalmaso and now I'm forgetting people's names, but Dalmaso and I'll remember in a moment. Bellatini. Okay, but those are amazing theorems. Okay, they're amazing theorems. And also we have people here at Hausdorff Institute that work on SPD. He's a famous person. He's here. Maybe he was even in these lectures. Conti, Sergio Conti. He works on these things. So he knows the ins and outs, and he's on site, okay, of these kinds of things. Yeah, so that's the thing. It's just we just test a point, and we see if there's a normal for which there's a jump, and then we ask, well, let's collect all these points and see what are they? And it turns out there's these beautiful. They lie on, they're countable components. They lay on these differentiable manifolds. Oh my goodness, So that's beautiful. It's truly beautiful.
Your fracture set, it depends on time, right?
Yes.
And in your weak formulations, when you're taking test functions, which are supported on this away from the fractures, doesn't it because your thing is compact set?
Well, and also we're supposing the fracture set never intersects these areas. Yeah, these are quiescent regions. Yes. And so there are many things that aren't mined yet. So I just gave you, as much as I know, but certainly, you also know, I didn't show it, but you also know that, for example, the normal traction on either side for every of these components of jump set is 0. You can show using test functions. But you have to, the experts probably can, prove it in full generality. I have to assume various things on the set, but then you can show, if the jump sets are regular, then you can show the traction is 0. But you would like to understand like how waves interact off the moving fracture set, and how moving fracture set is influenced by the waves that are hitting it, because they're carrying momentum and they're pushing the fracture around. Okay, so all of that structure and interaction I have not presented to you. Okay, for special cases you can, but for general cases I don't know anything. And even for special cases, I don't think anything's really been analytically worked out for that as well. So those are all open. Nice open questions that can be solved too, I think. For certain regular crack sets, you can solve some of these things analytically or theoretically. Well, any more questions? Okay, so we break for coffee. Thank you.